I meant on problem 39 to find the distance from a point to a plane, where the plane is described as the solution set to some algebraic equation. And I'm thinking that that distance is the component of a directed line segment in some direction. To remind myself, let me draw a plane out here in 3 space. Maybe I'll do it like this. And the idea here is if I have a point out there in 3 space, then the distance from that point, P, to the plane will be the length of this line, which, man, I'm picturing this line coming up behind the blue plane and making a 90-degree angle with that plane. So I was thinking that if I had some other point Q on that plane, then I could construct this line segment, direct line segment P to Q, like that. And then I'd have this right triangle in green with a 90-degree angle in it. And let's see. The idea is that there is a normal vector to the plane poking out this direction, and that I'm thinking about my drawing here. Well, the thing I'm worried about is the green line right here was meant to be perpendicular to the blue plane, and so was the red line, and my drawing doesn't seem to agree with that. So I'm not quite sure what to do. Should I start over with the drawing? No. I think what I should do is go back and delete this red guy and say what has to happen is actually that normal vector n has to point in the same direction as this line from P to the plane, which is orthogonal to the plane. And that's going to be the shortest line between P and the plane, is the one that's orthogonal to the plane. Okay, so this guy over here, PQ, PQ, here to here, he has a component which lies in the direction of n. Okay, and so naming things, let's call this guy Q. That is to say, I'm picking out a certain point on the plane. This guy was really easy, right? 13, 0, 0. If I substitute those 3 numbers for x, y, and z respectively, then I get a true arithmetic equation. Okay, so the component of the directed line segment from P to Q, the component along what I'll call n, and that n, oh yeah, right, you can get the n's, the normal vector from the coefficient of x, y, and z here. That is the vector 1, 2, 2, and I'm going to call that n. Okay, or, and let's see, that is PQ dotted with n hat, which is, okay, so first I need PQ, so P to Q, and then I take the components of Q and subtract the components of P, so 13 minus 2 is 11, 0 minus negative 3 is 3, and 0 minus 4 is negative 4, and I need to dot that with n hat. N hat is n divided by n, so 1, 2, 2, I should say, divided by the length of n, and so I'm going to have to divide here by 1, so I have to divide by the square root of 1 squared plus 2 squared plus 2 squared. 2 squared is 4, another 2 squared would give me 8, and then 1 squared, so that's 9. Oh, sweet. So square root of 9, that's just going to be 3. And this is 11 times 1 plus 3 times 2 plus negative 4 times 2 is minus 8 divided by the square root of 9, which is 3. Hey, this is pretty easy arithmetic. Maybe I'll go for it this time. 6 minus 8, that leaves me with a net negative 2, or 11 minus 2, which is 9 over 3. It's 3. Okay. The distance from this point to this plane is a simple 3. Fantastic. Oh, I also wanted to note the similarity between the distance from a point to a plane and a point to a line. For the distance between a point and a plane, you use the dot product from of PQ and a vector that describes the direction, the orientation of the plane. You can think about that. You sort of need to put this in absolute values because you do not want a negative number. Dot products can be negative, and we do not want negative distance. So we could do that. And when you are looking for the distance from a point P to a line, you simply replace this dot product with the cross product and this n hat here with a vector that describes the direction of the line. That might provide some economy of thought.